From the 3Degrees studio, I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders of the 3D printing industry. That was Abdalla.
Our vehicles are not at the volumes of automotive, so we're selling much more in that, reasonable volumes for additive. And we also have a commitment to our customers to support their parts. We support parts, for forever on some pieces of equipment. And seriously, I mean, you're talking 30, 40 years of supporting a piece of equipment. We have some of the most complicated pieces of equipment in the world. If nobody's seen how a combine works, Google it, go on YouTube. It's a factory on wheels.
Nassar. Abdalla is an expert in advanced and additive manufacturing with a decade of experience developing and leading cross-disciplinary R&D programs spanning MRL and TRL levels. Abdalla spent a number of years as a professor at Penn State and is now the Enterprise Additive Manufacturing Lead at John Deere. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Also, if you or your company are looking for materials, qualification, or general additive manufacturing support, reach out to the team through our website or via email at info@3degreescompany.com. All right. Abdalla, thanks so much for joining the show today. Really excited for the conversation here. So like we do with a lot of our guests, or really all of them, we like to start at the beginning in terms of where your career in additive started. So all the way back to kind of where were you born and what were some of those kind of pivotal early experiences that you can recall in kind of getting you on the track to manufacturing and engineering?
Oh boy. Well, happy to be here, Mike. Thanks for having me. So I was actually born in Egypt in a fairly large industrial city there. Moved to the US when I was fairly young, around 6 years old, 7 years old. But I remember sort of being interested in engineering at a very, very young age. So I still have memories of being back in Egypt. We sort of lived in a multi-story family kind of apartment. And you would go up on the roofs, and it was a big thing to fly kites. This is pre-internet, right? So you would fly kites and you would compete with neighborhood kids who are flying kites. I was too young to really participate fully, but my older cousins and other friends and relatives were doing it pretty aggressively. And I remember one day I had sort of a big insight, which was, hey, I see these bamboo rods up in a shed up here. Why don't we use those instead of, the sticks that we're rummaging for? Because that's what you did. You rummaged for things, or you found things wherever, and you kind of figured out how to put them together. And that was sort of one of the examples of just trying to identify a problem, coming up with a solution, and trying to make it work. Of course, I later got punished heavily for using those prized fishing rods that I shouldn't have been doing. But you would do all kinds of things like that. We'd make little guns powered by a little rubber band, and you would kind of crank it. But that's what kids did, kind of felt at the time. And so when I decided to go to university many years later, of course, I grew up in the US in Pennsylvania. I wasn't a particularly good student in high school. I don't think I ever made the honor roll. I really wasn't interested. Probably didn't even really start caring about math or algebra until well into my high school years. I joke with people sometimes that I didn't learn algebra until AP calculus, and that's when it clicked. They're like, this stuff makes sense. So, went to Penn State, chose the broadest engineering field that I could find, engineering, science, and mechanics, because I was interested in physics, but I was not brave enough to do a physics degree, and I was not nearly brave enough to do a mathematics degree. So I said, okay, engineering, science, and mechanics, it's as close as I can get to applied physics while it still is engineering. As sort of a senior in engineering, science, and mechanics, it's really geared towards having a very broad range of education your first couple of years, You take all the weed out courses, the EE, the basic electrical engineering course where half the class fails. You take all the EMEC classes, you take an insane amount of math classes, but your final year, it's sort of go specialize in something. Started working with a professor that I liked for no other reason than he was funny in class, who was actually doing some laser processing work. In those days, we were trying to do laser generated plasmas and laser sustained plasmas. Really started working with lasers at that point. CO2 lasers in those days, Nd:YAG lasers primarily. And then that emerged into, laser cladding was just one of the many laser processing techniques that I learned and worked with through my graduate career. And then eventually, when I was getting ready to graduate, there was this large AM center being stood up at Penn State at the time. We'd gotten a 5-year, $5 million grant from DARPA to establish the Defense Manufacturing Center. One of the people I worked with that does some work for laser, just laser processing. I'd help set up our laser lab and such, and so they were familiar with me and knew that I knew how to put systems together and knew a little bit about the physics. They encouraged me. They said, "Hey, come work with us." That was Sean Kelly was the person who hired me. I don't know if you've talked to Sean before, and Ted Reutzel there, both at the time, both at Penn State. And they brought me on board. And ever since, I've kind of been very heavily involved in additive manufacturing, primarily metals. Yeah.
I have a ton of questions. So first one, so say your course again at Penn State. So engineering,
science, and mechanics.
Okay. So that cuts across like mechanical and aeroastro engineering, kind of welding engineer. Like what does that encompass as the idea? Is it kind of
to
hit a little bit of everything?
Yeah, so the first 2 years, you literally take all the weed out courses.
Okay.
You take all, I remember EE, basic electrical engineering course. I remember many engineering mechanics courses. You have to take all the required math courses up to differential equations, matrix algebra, and then your junior year, you would take more math.
Yeah.
And then you would have a little bit of spatialization, maybe if you wanted to, but you take materials. So got really heavy into materials your junior year, and then your senior year you could take whatever. So your junior year, I think I also took the aerospace courses as well. So you take all the physics courses too, right? So you come out of that degree, and a few universities have it, right? So I think Virginia Tech has it. Some places call it applied physics. Some of the Ivy Leagues, I think, call it applied physics. Not applied physics, I'm sorry. Yeah, I don't remember what they call it, but they call it something.
Sure.
But it's the purpose is to expose you to a broad range of engineering problems. And the result is you come out, at least I came out, I didn't really care what the problem was. I felt confident in solving it. So to give you so my advisor for my PhD work, Judy Todd, who a couple of years ago retired as the head of ASM, very, very well known materials person. I was working directly for her, but I did my PhD qualifying exam, really focused on electrical engineering or electromagnetics. And to me, it was just it's you're working with the wave equation or the diffusion equation, and you understand the physics. It doesn't really matter what the particular problem is. It all boils down to some flavor of physics at the end of the day.
Well, and so you also mentioned kind of the term laser cladding. So for those who are listening that may not be familiar with that process, do you want to give kind of a quick primer on what that is?
Sure. So pre-AM, I would say there were two forms of laser cladding. There was powder blown or powder effect cladding. Essentially, you would use a deposition head, or even more simpler. You have a laser coming down. Doesn't matter what head you're using, and you're injecting powder into a melt pool somehow. Some people would use just a simple nozzle dispensing powder ahead of the melt pool as the laser was moving. And you had pre-placed laser cladding, which is now laser powder bed fusion. you would get a little scraper, scrape a thin layer of powder atop the material that you wanted to deposit, and then you would scan your laser over it, whether using a galvanometer or just by translating the laser over. Primarily, the reason to do it was primarily to add a wear-resistant coating or a corrosion-resistant coating on top of an existing material. Of course, with additive, you take that basic concept and you evolve it a little bit, and you're adding multiple layers, and you're controlling the actual path that the laser kind of travels from layer to layer. So metals additive manufacturing is really just an extension of conventional laser cladding.
And so you mentioned kind of you finished undergrad, kind of decision made to go to grad school. Maybe walk us through kind of that time frame and what you were kind of considering. Were you considering industry at all, or kind of once you got into the academic space really like that and decided to kind of pursue that further?
I would call myself kind of conflicted. The nice thing about my degree was that it really prepares you well for graduate school. The disadvantage is that nobody knows what it is. So I remember vividly, being a junior or a senior, going out looking for jobs and internships, handing in my resume, nice GPA, all these interesting classes. I remember recruiters looking at it, it's like, we don't have this in our system. So it wasn't very easy to get a job right out of an undergraduate degree. Um, I was also conflicted at the time. I had notions of potentially going to law school and abandoning this whole engineering thing, because I was also interested in political science and sort of law and arguments and logic and that field. But really, what drove me to go to graduate school was that there was a very nice integrated graduate program where I thought I could put in a year and get my master's. And two things happened. One, I started doing real research, and I liked it. And the other thing that happened was my advisor at the time said, "Hey, you're doing really well. I'd really like to support you for a PhD." And I was like, okay. And then the final thing that kind of tipped it over the edge was that I was awarded a NSF Graduate Research Fellowship, which they essentially give you your PhD and pay you a little bit more than a regular student. So quite honestly, it was I wasn't destined to go into research by any means, but things kind of just lined up where I had the interest, the capability, and it was a path that I could see that I was happy to take, and I was interested in taking, and people were encouraging me, right? So my advisor was encouraging me. Dr. Steve Copley, who also I worked closely with at Penn State, was encouraging and very helpful as well. And everybody really that was around me was saying, "Hey, you should consider this. You should really pursue this."
And what's the timing in between kind of the undergrad and PhD, like when the AM facility opened? Was that at the beginning? Was that towards the end of?
It was right at the end. I was literally, within you're about to finish your PhD, a year in advance. That's when you have to write your thesis, and that's when you've passed your comprehensive, and you got to get things written. And right at that same time is when they were planning for the facility. It was kind of opening up. Penn State had some additive equipment long before then. It had been involved in additive before that time as well. But that was really kind of a step change. And for me, I wasn't really looking at the growth potential. Again, it wasn't. You don't know. At least at my age, I didn't know that this was going to be the best path or the most successful path or whatever. What I thought was, I'm doing something cool. I like it. This also seems cool. I'll do that.
Yeah. And had you seen, I mean, you'd been working with kind of laser cladding, so you'd seen kind of additive processes. Talk about kind of like, when you say you thought it was cool, you thought it was interesting, like what about it was kind of grabbed your attention? What about it was kind of motivating you to kind of dive deeper into the technology, into the industry, into the field?
Yeah, that's a good question. So maybe I'll step back just a little bit, maybe a little bit more history, because that kind of explains my thinking. So I remember, when I started doing research in the lab that I ended up getting my PhD in, it was a fairly new facility, and we were expecting this big 5 kilowatt CO2 laser to come in any day now. For the first year, nothing happened. Everything was delayed. So I had to do a bunch of modeling work, and I realized I don't want to do modeling, at least not heavy modeling, for the rest of my career. And then one day this laser shows up. Okay, this big laser in a big crate, and then all these stage systems show up. And I kind of look at the postdoc in the lab and like, what the hell do we do with this? So I'd learned in that sort of second year how to set up all this equipment, how to arrange it, how to control the laser parameters, and we had to literally set up everything. I remember aligning, 7 mirrors vividly, 7 copper mirrors to get the beam from the laser into the chamber. And that is painful. But my point is,
That's high quality grad student work.
oh man, is it ever? But my point is, I knew that by controlling, the laser settings, the laser parameter, the way you were doing your process, and doing all that work to control the things that you don't want to do as a graduate student, to define the program, to drive the stages, etc. You can influence the resulting material very, very drastically. You could do really cool things. And so when additive was coming up, and I learned more about it. Of course, I knew about additive because it was a chapter in my laser processing textbook that I had read. But what really drove me to it was you can control so many more knobs than you could ever control with a conventional process. I can bake the material, I can change its chemistry, at the same time that I'm changing its processing conditions, at the same time that I'm designing a new geometry. So I was just blown away by the sort of the possibilities of what you can kind of do with this thing.
And so you finish up your PhD, this facility is just opening or kind of on the verge of being created. Kind of what was the next step in your career track?
Next up, so here I am. At that point, that was sort of a postdoc appointment for a year, and my plan was year postdoc. Let's get out of state college as fast as I can. Got some job offers, but as they always do, Happy Valley kind of pulled me back in. I started getting a little bit of success, right? So I started writing some papers, going to some conferences where people were complimenting me on what I was doing and what I was writing. And I knew the capabilities that we had at Penn State versus what some of the other emerging capabilities around the country were, just by being exposed at the conferences to what was happening around the country. And at that point, that's when I became sort of more sort of logical in my thinking and my planning. And I looked around and I said, there's no better place for me to do the type of work that I want to do. So I took on a position, and they wanted me, right? Because you don't get these things unless they want you. I took on a position of an assistant professor, assistant research professor with the applied research lab at that point, and then just started rotating the hamster wheel of academia and research. You get some funding, you write some papers, people get interested in your work, you get more funding, you go out, get sponsors to know who you are. They appreciate your work, give you more funding, and then next thing you're an associate professor, and you've got appointments with some of the other academic departments, and you're doing research with people across the country. That's kind of just, you kind of keep rolling that snowball downhill, and it keeps growing.
And I imagine you were teaching as well.
Yeah, so I was. So initially, when I started, I was teaching laser materials processing, which was a really, really nice course. I had inherited some of it from Vlad Simek, who's if you read some papers on melt ejection, he was the one who kind of popularized some of those notions that we know today as sort of keyhole formation and melt ejection. But he had left Penn State, so I kind of revived that course back up, took it over, and taught that for a few years, and then the additive manufacturing and design program at Penn State got going, or was proposed, right? So really led by, Tim Simpson and Rich Martikanis at Penn State and many other folks, proposed to teach this course on the foundations, the scientific and engineering foundations of additive manufacturing. Again, really a math heavy, physics heavy course looking at all these concepts that many folks already knew from the welding literature, and then kind of just translating them over, showing them to a new audience, and of course pulling in some of the new data on metals, and we got into polymers as well at that point. So I taught that course for several years. Oftentimes I would co-teach it with Ted Droitzel at Penn State or somebody else, because it was sort of a big course. It was a 4-credit course. We taught it at a graduate level, and we taught it to both full-time residential students as well as a lot of industry folks. So it was about 50-50, and we were teaching it simultaneously in class, and it was sort of live streamed or recorded to the remote audience as well. So that was a really good experience as well. I really enjoyed my time teaching.
And through that, I mean, obviously you're dealing a lot with industry through your teaching, but how important was it to have, as a professor, to have some of those industry conversations, industry connections and projects? Was that additive seems to be kind of a natural vehicle for a lot of these cross industry, cross academia, consortium type of projects? Was that kind of something that you leveraged while you were at Penn State?
Yes. And the reason is, so different universities operate in different ways, right? So my home department was the Applied Research Lab at Penn State, which is part of Penn State University, but it's really its own self-contained unit where it's a research lab for the Department of Defense. Without going into a lot of detail, what that means is that we were on what's called soft funding, meaning that my salary was not covered by the university. So most professors, their salary are covered by their department. They teach a few classes. That's kind of what pays their salary, and they could get some extra money to teach summer classes. We didn't operate that way. So I was entirely self-funded. And not only that, by the time I left, I had a team. So I was a department head, meaning I had 7 people who reported to me. So to stay afloat, I don't want to give the actual number, but it was well over $1 million to kind of keep the system going, at least my individual group going. So what that means is that I was doing a lot of programs with the Department of Defense, other government agencies, as well as with a lot of industries. Sometimes it will be collaboration on a government project where it would be a big group, Penn State ARL, a bunch of defense contractors going after a specific research topic. Sometimes it would be direct industry funded, where a company would come to us, typically a large company, many times small companies as well, where they have a problem. You would help solve their very applied problem. That's a little bit different than how a lot of other universities or professors kind of operate. What was nice about what I was doing is that I was doing sort of both the basic science work, NSF grants essentially, or other, types of grants that do basic science. And I was also doing very, very applied research. I mean, I'm talking like TRL 8, where you're developing products and systems and software that's gonna be put into the field. It's gonna be operated. So it was a really broad exposure to both the basic science and a lot of great work with some businesses.
Awesome. And so what you're clearly not at Penn State now. What was the transition like out of academia into industry?
It was a lot easier than I think some people had scared me into believing. I think the big difference now, being in industry, and I'm now with John Deere, and John Deere is a good organization, and maybe that explains the ease of the transition. Is that a lot more than trying to look for problems or trying to identify gaps. I'm really looking for solutions. And I don't care if our organization solves that particular problem or has a solution that's internally developed, or if we can buy it. Almost always, it's preferable if we can just buy it. So much of my research focus now is, and I'm still doing research and development work, but a lot more of it is now, who do I find to solve this problem for me, rather than at a sort of a university or a research lab setting where you're really looking at developing things in-house. Even if, that guy over there or that gal over there has a solution to this existing problem, wait, I could do it better. And so you want to build that internal capability, and you want to solve that problem, and you want to fill a gap, and you want to do it in a clever and unique and different way. Within industry, my real focus is, we have real problems. Additive can help address many real needs for us. I don't care if it's the best solution. I care that the solution works. Does it work? Is it cost effective? And it's kind of a change in mentality, which hopefully I've kind of adapted to.
And can you talk a little bit about John Deere's philosophy when it comes to additive? It's one of the most recognizable brands in the world, really, and in a number of fronts, in agriculture and many other industries. But why is additive or advanced manufacturing technologies important to you guys?
Sure, yeah, absolutely. And there's been lots of kind of public presentations on this. So nothing I'm going to say is kind of secret. Deere has been involved in additive for over a decade now. We bought our first powder bed fusion machine, laser powder bed fusion machine on the metals in like 2013. We have hundreds of polymer printers throughout the enterprise. We have public relationships with suppliers that are producing serial additive parts for us. And why would we do that within Deere? Well, Deere is a easily top 100 of the Fortune 500 companies in the world. Huge operation, many units spread out across the globe. We have a very high mix, lowish volume operation. We're not automotive. Our vehicles are not at the volumes of automotive, so we're selling much more in that reasonable volumes for additive. And we also have a commitment to our customers to support their parts. We support parts for forever on some pieces of equipment. And seriously, I mean, you're talking 30, 40 years of supporting a piece of equipment. We have some of the most complicated pieces of equipment in the world. If nobody's seen how a combine works, Google it, go on YouTube. It's a factory on wheels. It's insane. We have applications that extend all the way from large agriculture, which is what we're kind of known for. We have road building, we have construction facility, we have forestry. We develop the implements that go at the end of some of our forestry heads. We have a battery business. We build our own engines. We sell engines to others. We have our own electronics. We sell our electronics again to others. And the type of electronics, the types of systems, and the types of operating environments that we are working are really kind of unique and really demanding, much more demanding than maybe some of the typical applications that folks would think of if they just, are only familiar with something that you buy from one of the big box stores to cut your lawn. So additive can solve a lot of potential problems for us, both in our low volume serial production kind of workflow, as well as in our service parts workflow. And there are some other applications to additive that aren't very sort of clear, that I can't talk about at the moment, but there's lots of other applications where we're leveraging AM today.
Yeah, maybe, I mean, certainly take experience from your time at John Deere, but maybe also any perspective that you had at Penn State. But I mean, you mentioned kind of the 10-year mark where there's a lot of DMLS now kind of proliferated through a number of different industries. But it seems to me like with larger companies, like the John Deere's, another of the world's, like this 15 year ago mark where there was a big exploration exercise, right? Like, okay, we're going to dip our toe in. We might have a center of excellence, or we have a couple of different facilities going rogue and try and do some of this additive work, R&D. Many companies have kind of consolidated that into a center of excellence, or like, hey, we're going to have one node where AM flows through, and that's how it goes, versus, okay, we have 20 different plants and each plant is going to have their own additive flavor or whatever it may be. How have you seen that evolved? And to the extent you could talk about it in John Deere, great, but more just generally in your experience, like, it's been around for a while. Like, there has been kind of this push of experimentation. Like, how is it kind of starting to settle out in terms of strategies that seem to work, and getting the technology adapted in the right places at the right TRL level or adoption level, right?
I think it's a great question. And I'll step back from it a little bit and kind of go through. Let's focus on laser powder bed fusion of metals for the moment. And what I'll say is that I did an analysis recently of looking at the cost of making a part via laser powder bed fusion. And if you go from like 2010 to let's say 2015, 2016, what are we talking about? We're talking, at least if we take the largest, holder of market share in that space, EOS, we're talking about EOS M280, EOS M290. And those machines, as well as just other machines from the other companies, I'm not saying anything bad about the other companies out there, they're all great, is they were really focused on really making their parts as high quality as possible. They were focused on aerospace, medical, using things like titanium, nickel alloys, very expensive stuff, very slow processes, not high productive machines, not machines set up to work in what I would call a typical sort of automotive or heavy industries workflow. Only in the past, I would say 4, maybe 5 years, have we seen what I would call highly productive machines where the cost is coming down. And the cost has appreciably gone down in terms of the cost to make an AM part. The CapEx, the capital cost of these pieces of equipment, has not gone down. In fact, it's gone up. But if you compare what you can do, sticking with EOS for a moment again, just for baseline comparison, if you can compare what you can do on an EOS M400 or an EOS M300 versus what you can do on an M280 or an M290, it's night and day. Even though the machines are much more expensive, the number of parts you can crank out and the speed with which you can crank them out is a really big game changer. Same thing, throw out another provider just so I'm not biased, like SLM. If you look at their NXG platform, undoubtedly, if it does what they're saying it will do, and I think they might have machines out to some customers already, the cost of that machine is a lot. It's a very, very expensive machine. But again, productivity is very, very high. My point is, a lot of the early exploration was just that, was let's see what this technology can do. Let's vertically integrate it. Let's see, let's follow the technology. We're not going to invest in it yet, but let's follow it. So we don't want to be behind when it takes off. The thing that always prevented it from taking off, in my opinion, is cost. And I made this comment at a conference, I think it was an American Makes event or a NIST event recently, which was, the aerospace birthed additive. It really did. Meaning that's where we saw the first big production cases, and that's really where we saw things happen. But aerospace is also killing additive. And what do I mean by that? If we focus on these very expensive alloys and we focused on making parts that are 99.967 8% dense, and we focus on hipping all these parts, it's never, ever, ever going to be used for mass production, for real industrial level stuff. And if you can compare the sort of the opportunity, the market size for aerospace versus all the other industries, aerospace doesn't turn out to be that big. And so my point is, only now are we seeing some of the companies, some of the organizations who are producing machines kind of realize. And some of them did realize a long time ago, but got in too early. And getting in too early is just as bad as being wrong. They got in too early where people weren't happy to adopt. But now we're seeing the right alloys come on the market. We're seeing the right machines with the right sizes and the right productivities that we can make a reasonable business case around AM. I can't talk specifically about our strategy. We have a strategy we're developing, but I really can't talk about what we're going to do strategically at Deere. But what I could say is, if you look at other companies that have really taken additive seriously in our space and in similar spaces, it's only been in the past 3 years, maybe 4 years. Whether you're talking about the big automotive companies, all the major investments have really only happened the past couple of years, and that's not surprisingly has coincided with the market now being a little bit more mature and mindful of the needs of other industries besides medical, defense, and aerospace and space.
Yeah, fantastic points. And so, kind of tying the conversation together with the last couple of questions, kind of what are you excited about in the next kind of 6 to 8 months in the industry, or even kind of your job as you've transitioned out of academia into industry? Like, what are kind of one or two things that kind of get you up in the morning, kind of get the juices flowing in terms of working on what's next?
Yeah, well, we haven't talked about polymers much, but I'll say polymer additive has matured to the point now where it really is for some of these technologies competing with injection molding for low volume production. Um, I'm really excited about that. I'm excited about the technologies that are already on the market and the technologies that some organizations are working on that they've been promising to bring to market for a few years now, but hopefully will come to fruition soon. And if their promises and their technologies really are what they're saying, then we're going to see things change radically in the polymer world. You're going to see injection molding being displaced in a real way, and other sort of polymer-based processes. Um, on the metal front, I first started out really, doing a lot of directed energy deposition. I think directed energy deposition is still makes a ton of sense for certain applications. I don't know, maybe I shouldn't say this, but I'll say it anyways. I don't know if directed energy deposition of huge structures will ever make sense. But I think directed energy deposition, whether it be with laser or wire arc, um, or even the cold spray stuff that folks are doing, makes sense for targeted use cases where you can deposit a small amount of material rapidly for a specific application.
Awesome. So on the polymer side, is that more on the powder bed, or are you more interested in the filament, or somewhere in between with SLI?
So filament material extrusion AM has revolutionized the way we do tooling in our organization. It really has. And I think that's true of a lot of other organizations. That photopolymerization is still of interest. We see it being used in some consumer goods already. It has some inherent issues with UV, as you can imagine, and some other inherent downsides. But it's a promising technology. But what we've seen, I think, in the past, again, couple of years is that powder bed polymer technologies have really taken off. Even just the volumes of polymer powder sold compared to the volume of resin is now reaching the point where you're selling a lot more powder than you are resin for photopolymers. So I'm really excited about powder bed based processes.
Awesome. So last question, more of a fun question. Um, what's a book or a paper or something that kind of gave you inspiration throughout your career, whether that's professional inspiration, personal kind of growth inspiration, anything come to mind?
Yeah, books. So, yeah, I can give you a list of books. So, the first sort of when I was doing my PhD, the Feynman lectures on physics, wonderful, wonderful series, even if you're not a super nerd. But what a great way. You don't really understand physics until you've read some of his textbooks and lectures. They're really fantastic. Um, right now, I mean, Sapiens is a really good book. It really helps, at least it helped me kind of realize how much of the world is based on just constructs and notions that we develop ourselves. Um, Vikal Smil, I hope I'm saying his name correctly. He has a series of books out, things like How the World Really Works. and I think Energy and Civilization. It's a series. What he really does is he looks at problems and tries to break them down into sort of approximate math equations. So, for instance, the question of, um, what is nuclear energy safe? You can mathematically diagnose that and say, is it safe, or is it, how many deaths does it cost per year? Does it make sense or not? Things like, what's the most important technology? What technology has saved life? Things like, ammonium-based fertilizer revolutionized the world. Um, so I think those are 3 or 4 books that I say. Go out and read each one of them because they're fantastic.
Awesome. Cool. Well, thank you so much for the time today. Awesome insights. Thank you so much for sharing and sharing your story. So look forward to seeing you, I'm sure, at one of the upcoming AM events in the next few months, and we'll talk soon.
Yep, I'll see you on the circuit. All right, thanks, Mike.